Hi, welcome to tutorial 3.5 part 2 on finding empirical formulas. And this time we will find some formulas. We'll do two examples from combustion analysis. So first of all, let's get our orientation or get our bearings relative to the previous tutorial. In the previous tutorial, this is how we worked on the samples. We said imagine there was a sample and that I could pull the carbons out of the hydrocarbon and the hydrogens and place them on separate scales. We did that in order to come up with that mass ratio of 80 to 20, but we didn't talk about how you actually do that. Do you actually pull carbons away from the molecule and can separate them out nice and neatly in one box and hydrogen the other? And the answer is yes, at least a little bit indirectly. So the next slide kind of shows how we actually do this. So what's going to happen? The sample is sitting in here and it's in a furnace, and we're going to burn it in the presence of oxygen. So we're going to introduce this new material to our sample. What's going to happen is the chemical reaction will take place, and all the carbons in the sample are going to join with these oxygens and turn into carbon dioxide. And all of those are going to be separated out into a carbon dioxide trap. A picture that I'll show you in a second. So in effect, we have separated out the carbons from the original molecule. The only problem is we've also added some oxygens in the process. What happens to the hydrogens that are in the original sample? Again, they react with the oxygen in the process of burning, and they get pulled out and they get attracted or get attached to this water trap in the form of H2O. So again, we've got the hydrogen sitting there, but they now are, it's not just hydrogen, it's hydrogen in the form of water. So what we have to do is kind of manage the fact that we've got these extra oxygens here mathematically when we're trying to figure out the empirical formula. So here are the steps that we're going to go through. One, by counting how many carbon dioxide molecules are formed, we should be able to figure out the number of carbon atoms that were present in the original. So we'll count these guys. We're going to divide their mass by the molar mass of carbon dioxide. That's going to tell us how many carbons were in the original. And then we're going to do the same over here in step 2. We're going to count how many water molecules there are produced and simply say, okay, there must have been twice that many hydrogens in the original because every water molecule has 2 hydrogens attached to it. The last little thing is that what if the total mass that we find of carbon and hydrogen does not account for the original mass of the sample? We say, oh, there must have been something else in there. And on the assumption that there's exactly one other element that is also part of the particular molecule, we should be able to figure out the number of the grams and therefore the number of moles of that substance as well. All right, so let's try this out with a real example, but first let's kind of look at the apparatus, how it is actually would actually appear in the lab. There's a furnace, and here's where we're going to place our sample. Oxygen will come in from the outside, so there's some kind of hose attached here with oxygen, and as this thing is burning, these oxygens will burn up the carbon and the hydrogen to turn them into carbon dioxide, which gets trapped over here. And all the water gets trapped on the other side. So you can imagine the water molecules flowing through this green trap and eventually getting trapped over on the water side. So these substances will weigh more than our original material that we put in the furnace because the oxygen is going to be added to the carbons to make the carbon dioxide. The oxygen will be added to the hydrogens to make the water. If there's some missing mass at the end, we can say, oh, okay, the other substance, the other element that's in our sample, we should be able to figure out by subtracting off the missing mass. Okay, so first let's get our bearings here in terms of the template from the previous tutorial. This is 3.5 part 1. And the way this worked last time is we said, imagine I already know the mass ratio. I know how much carbon there is to hydrogen to oxygen in a sample. What we'll have to do this time is come up with these numbers through some data from the lab. All right, so what are we going to do? Where are we going to get this carbon number from? Well, from the mass of CO2. You say, oh, that's not going to be too bad. If I know the mass of CO2, I can get the number of molecules of CO2, and from there I should be able to get the mass of the carbon. This hydrogen mass is going to come from the water. Figure out how many waters you have, and then look and say, oh, well, there's 2 hydrogens for every water, so I can figure out how many hydrogens we have. The missing mass, then, we're going to subtract the sum of the masses of these two to figure out how much is missing to get the mass of the last component. In this case, it'll be oxygen. Actually, in both examples in this tutorial, it'll be oxygen, but it might be something like nitrogen, phosphorus, or whatever. Okay, let's do this with some real numbers. So let's pretend that we have a sample that weighs 460.69. Let's assume it's an alcohol so that we know it contains nothing but carbon, hydrogen, and oxygen. And imagine that when it's burned up, it produces in that carbon dioxide trap 880 grams of carbon dioxide. Can I figure out what mass there was of carbon in the original? You say, oh yeah, I think I can do that. First, I'm going to figure out how many carbon dioxide molecules are represented by the 880 grams. CO2 weighs how much? Carbon weighs 12, each oxygen 16, so that comes out to 44 grams per mole. So therefore, if I divide the 880, think of that as like a pile of CO2, by the 44 grams per box or per mole, there's 20 moles of CO2 that we must have produced. I said, oh great, so that's going to tell me how many CO2s I have. Is that the same as the carbon number? Well, I think it is. If you look at the formula, a single carbon sits in the middle of every CO2. So if I know how many CO2s there are, of course I know how many carbons there are. It's exactly the same number because there's one carbon for every CO2. So I do know how many carbons there were in the original. There must have been 20 moles. I also know that carbon weighs 12 grams per mole. So if I multiply the mass of carbons, the molar mass 12 by 20, that tells me how much mass there must have been in the original sample in the form of carbon. So there were 20 moles of carbon at 12 grams per mole, 240.22 grams. I say, great, I can now fill in the first two parts of that kind of template that we were using to work things out in the previous tutorial. These two parts here, I got 240 grams of carbon in the original. 20 moles is what that turns out to be of the original sample. Now I'm going to do the exact same thing with water. Say, all right, how much water was produced in this particular experiment? Remember, the sample weighed 460. We produced 540 of water. And again, don't be confused. 880 plus 540 is way more than 460 because we've added the oxygen with that hose that we attached and when we were asked to burn up the hydrocarbon. All right, how do I figure out the amount of hydrogen? I'm going to divide the 540 by the molar mass of water. What is the molar mass of water? It's 16 plus 2 is 18. So that water weighs 18 grams per mole. If I divide 18 in the 540, think of a box or a pile of H2O sitting there. There's enough stuff there to fill 30 boxes of water. 540 divided by 18 comes out to be 30. All right, is the number of water molecules, the 30, the same as the number of hydrogens? Well, not quite, because unlike the CO2 example here, there's 2 hydrogens in every single water molecule. So if I know the number of waters, there's actually twice that many hydrogens that must have been present in the original sample. That's easy enough to find. 2 times 30 is 60. Now that I know how many hydrogens that I had, to figure out their mass is straightforward. I multiply the grams per mole, the molar mass of hydrogen, times the number of moles that we have. So that comes out to 60.48. And now I can fill in the second part of that table. 60 moles and 60.48 grams for the respective amounts of hydrogen in the sample. We're almost done. Now we have to look and say, okay, how do I get the oxygen? Well, if you add these two up, 240 plus 60 is 300, and with the decimal 300.7. So the entire sample so far, according to us, only weighs 300, but it weighed more than that. Remember, it's 400 something. So that missing mass, the extra mass that's missing, must have been this oxygen. So all we do is subtract these two numbers off, take the 240 and the 60, add them up together. Their combined mass is 300.7, and subtract those from the 460 gram sample that we had to begin with, and it comes out to 159.99. Sorry, I didn't put all the decimals here, so this should read 460.69. Same up here. I'm not sure why I just dropped those the 0.69. In any case, this is the right number. 159.99 grams is the missing mass. That's what the oxygen weighed. If I put that on the table, I'm essentially done. I've got the mass of oxygen. I know to divide this by its molar mass to get the number of moles. That is, divide this by 15.999. I have a ratio 2 to 6 to 1, it looks like. Divide it all by the smallest number to make that obvious. And I got the empirical formula. It's C2H6O for this sample. I hope that was pretty good. I want to do one more though, just because these numbers are a little bit too clean, a little bit too perfect, and not quite fair to what you might actually get in the lab or on the quiz. So let's look at some smaller numbers, more like what you would actually get in an experiment. Same exact process though. So this time we have the combustion of 0.255 grams of some alcohol, which means that again has only carbon, hydrogen, and oxygen. The carbon dioxide produces 0.561 and 0.306 of water. Let's go through the steps. I've got the 0.255 gram sample. The carbon dioxide sitting in that trap is 0.561. I have to divide it by the molar mass of carbon dioxide, which I know is 44.009. 12 plus 32 is 44. Dividing 0.56 by 44 gives me this very small number, 0.01275 moles of CO2. I go through the same thought process. Is that the same as the number of carbons? Yeah, every carbon dioxide has a single carbon, so that number of moles of CO2 is also the number of moles of carbon, and they weigh 12 grams per mole, so the total mass of carbon is 0.1531 grams. I'm ready to put that in my table. So the original sample contained this many grams of carbon, which is this many moles. We're ready to move on to the water. We're going to figure out the mass of the water in the trap, divide by its molar mass. How much water was in the trap? 0.306. The molar mass of water is 18. I divide them. I get the number of moles of water. This time we're careful. We say, yeah, but that's not the number of moles of hydrogen because there's 2 hydrogens in every water molecule. So I have to double this number to get 0.03397 moles of hydrogen. But once I have it, I just multiply by 1.008. That is the molar mass of hydrogen to get the mass of the hydrogen in the original sample. Multiplying the 2 gives me 0.03424. I'm ready to fill in the next part of the table. All right, here we go. Now the missing mass. If you look at these 2 numbers, they don't add up to 0.255, but what? 0.15 plus 0.03 is 0.18 something, 0.187 something. Clearly not the 0.255 that the original had, so I'll have to subtract the sum of these from the original to figure out what the mass of oxygen was in the original sample. So let's add those up. What do we have? 0.15 plus 0.03 with decimals, it comes out 0.1873. Subtracting that from the mass of the original sample, the 0.255. Not 460, that's a typo. Subtracting from, this should read 0.255. Sorry about that. Oopa. That's just, this is just a typo. 0.255 minus 0.1873 gives me the mass of the oxygen. Okay, we're ready to fill in this last part of the table. 0.06766 grams. What do I do with this? Divide by its molar mass, that is divide by 15.999, and I get the number of oxygens. What do I do with this last step? Find the smallest number of these 3. This is the smallest number, so we're going to divide all of them by 0.004299. Hope to get a whole number ratio. We do 3 to 8 to 1 with a little bit of rounding, and the formula we have is C3H8O. All right, so that was it. A little long-winded, but I think having 2 examples was probably worth it because the numbers are harder to manage. So look through the PowerPoint on your own slowly if you need some practice getting through it, and then just try the ones online and see how you do. And we'll work through some of those together in class as well. All right, good luck with this. I'll see you in class. Thanks.